Hello and welcome to AIAIART Lesson 3. This is a re-recording for various technical reasons. And I'm in a different locality, staying with some relatives at the moment, so please do excuse the noisy birds and monkeys and things in the background. We'll try and do the best that we can in the circumstances. So before we dive into today's notebook, I'm making a copy of it to edit for this lesson, and I encourage you to create your own copy to save in your drive and modify. Let's quickly recap what we covered in the previous lessons. So in lesson 1, we did some introductory concepts. We learned how to create and manipulate tensors, working with images as tensors, and doing these basic operations, reshaping, indexing, and so on. And then we got introduced to this idea of gradient descent, the idea that if we can define a loss function, some measure of how well we're performing, and some function or set of parameters that produce some output, then by looking at the loss and specifically by finding the gradients of that loss with respect to our parameters, using automatic differentiation, we can gradually update our parameters to improve that loss. So it's an iterative process, but we can gradually converge on some better solution. So that was a really cool insight. We tried it out on a very simple, just fitting a straight line to some data. And then we sort of went beyond that, sort of seeing that the same kind of training loop, zeroing our gradients, getting our output, finding our loss, using loss.backwards to calculate the gradients, and then optimizer.step to update our parameters. The same approach worked for much more complex situations. So in this bonus section, we used clip as kind of a black box. We said we can somehow compare images and text. So let's start with an image as a set of random numbers, and that can be the parameters that we're going to optimize. And over time, we're going to apply the same sort of idea of gradual optimization. We're going to gradually update that image so that it looks more and more like our text description. So that was a cool little piece of magic. And then the next lesson was, okay, how do we build on this? So lesson 2, learning representations, but also just getting familiar with working with deep neural networks in PyTorch. So we started with building some very basic neural networks. How do we chain together different layer types, linear layers, non-linearities, and so on? And how do we train that? And we saw the training loop is actually very much the same, where the parameters are now just the weights of the different layers in our network. And we're just slowly optimizing these by measuring our loss and updating the parameters. And once again, this network can learn sort of simple patterns, but it can also, if we use, especially if we use some additional tricks for learning parameters efficiently across images, we can train a network to do something like image classification. Same ideas. So we saw convolutional neural networks, we saw convolution and pooling in this little interactive example, and then we trained a convolutional network, which we defined with convolutional layers and pooling layers. We trained this to do image classification and do it fairly well. So that was a nice introduction to sort of building networks from the ground up. Then in section 3, we looked at how do we use the things that have been learned by these more advanced networks, right? This is VGG16, sort of larger, but still fairly simple convolutional neural network. And we said that as we go deeper and deeper into these networks, the types of features they learn tend to be less and less sort of edges and colors and more sort of higher level concepts. And by taking the outputs of different layers, we can kind of abuse those representations artistically. And so this little demo was style transfer, starting from some image and optimizing it slowly. But in this case now we have a loss that's some measure of stylistic similarity to one image and structural similarity to a different image. And over time we end up with this sort of style transfer process, and we showed it in a few different ways. As a neat little trick that we can do to use the representations that these networks have learned for our own ends. And then right at the end of this network, in a sort of little bonus section, we came across something called an autoencoder. And the idea behind these is to start with some input and to compress it down to some hidden representation, and then try and reconstruct the original image just from that hidden representation. And this is a pretty neat trick if you can pull it off, because it enables things like really high compression rates, and it also forces these different parts of the network to learn how to really efficiently generate images from this really small representation and how to create that representation efficiently. So by having a loss comparing the output reconstruction to the original image, over time we can train these networks to get really good at reconstructing some input. Now we saw that they could also be used for generation if we just give a random value as this hidden representation, but that doesn't tend to work too well because of various limitations in how they're trained. So in today's lesson, we're going to build on that. We're talking about GANs and CLIP, which together are sort of the, I guess, the state of the art in terms of text-to-image generation and the kind of current zeitgeist in the AI art scene. You see a lot of images generated with this technique. And so we're going to break down these two cool concepts, one after the other. Oops, I'm going to work in my copy of this notebook rather. So yeah, we're going to be exploring this, and then we'll try and sort of understand both of these on their own, and then try and understand it combined. So let's begin with the idea of GANs. So I guess the theory behind these generative networks, if we start with this autoencoder which we saw previously, our loss function is just the reconstruction loss. How well does the output match the input? And this works okay if we just want to be able to reconstruct some input. But in a GAN, we often want to be able to generate new outputs. And so we introduce a second kind of sub-network called the critic network or the discriminator. And the idea here is that we will start with a random Z or encode an image. We will generate back some fake or generated image. And then the discriminator network will try and distinguish between these fake images and some real images from a training data set. These could be images or paintings or whatever. And so we are the discriminator is continuously trying to get better and better at telling which images are fake. And the generator, the loss that we use to update the generator is how accurate the discriminator was. And so it learns to fool the discriminator better and better. And so these two kind of are adversarial. That's why it's called a generative adversarial network. And while it's training, the generator is getting better, then the discriminator has to do better to tell between the real and fake images. So then the generator has to make even more realistic looking images to fool the discriminator. And ideally, the two kind of feed off each other and get better and better in tandem. And we end up with some really nice outputs. So that's the dream. Now, there's some trickiness to actually training a GAN. Here's another representation, by the way. Random vector in, generator model makes an image or images, some real images, and these fake images are fed to the discriminator. Then the classification loss is used to update the discriminator and the generator. So yeah, we can see this in action in this little interactive GAN lab demo, and you can try this out. It's quite neat to see the sort of flow, right? Once you set the simulation going, you see the generator trying to create data that looks like the real data from noise. You see the discriminator getting better and better at distinguishing between them, and over time, the generator learns to generate really plausible distribution of data. Whereas if you were to reset the simulation or use a different distribution, you could watch it then start out really bad. The generated data is going to be way different from the real data. The discriminator is going to do really well, and then it slowly updates. So it's a fun little tool, but it does chew up your RAM, so make sure you clear the output before you move on. Yeah, so we're not going to go into training a larger generative network on, say, high resolution images, because there's some caveats that often crop up in GAN training, which I've pushed to a section later on in the notebook. So for now, instead of playing around with trying to train our own GAN, we're going to instead use a really modern, fancy architecture, and we'll explore how it differs from our kind of base GAN architecture, and then also how can we use it for our own ends. So the one I've chosen is VQGAN, very popular in the AI art scene. They have a really good set of resources, so you can go to the Taming Transformers website and you can check out the actual paper itself. And if you look at this architecture diagram here, you'll see that a lot of these components are very much what we've talked about with reference to GANs, right? You have an encoder into some compressed representation Z, you have a decoder that blows that back up to an image, and you have a discriminator which is trying to tell real from fake, which is used during training to make sure that this decoder part especially generates very realistic looking images. What they've done is, in addition to this, they've added this quantization step. That's why it's called vector quantized GAN, which transforms our continuous Z into some set of discrete tokens. And you'll notice they also split the image up into patches. So we have this kind of sequence of tokens. And wherever you have a sequence of tokens, the transformer model suddenly becomes a really powerful tool, because transformers work on sequence data. and their goal, they can do things like predict the next token in a sequence or do sequence-to-sequence translations. And so by doing this quantization step and framing this as a sequence modeling problem, they can suddenly take advantage of transformer models to do things like image completion, depth map to image translation, segmentation map to image translation, pose to image, and so on. They can do these really cool image manipulation tasks using transformers. Now, we're not going to worry too much about the transformer side of things. That's a bit beyond the scope of this course, but we will work on how do we use the encoder and decoder parts of this network, and how do we work with this to generate images. So this setup function here is going to download some pre-trained weights, these checkpoints, and by the way, they're hosted on some university server, but it's nice to copy them to your Google Drive so that you can comment out these lines, and instead of downloading them each time, you can instead just copy them across from your drive. You can mount it in the files panel on the left. So if you're going to be running lots of experimentation and you're going to be rerunning this notebook often, I highly recommend moving over to storing the weights in your drive. It also means that if this particular server goes down, you're not stuck. And then there's a few other convenience functions in here, loading the VQGAN models and so on. So we'll just let that run. It's 500 megabytes out of 900 megabytes downloaded, so this is a very large model. But once it's finished downloading, we'll be able to load it up just with a single line of code, because that function does all the hard part for us. And it's just looking at this file for the configuration and this file for the weights. And if you look around at other notebooks, you'll see there's pre-trained weights available for various different training data sets. I think there's one on faces, there's one on WikiArt, there's a few different image data sets. So we'll stick with this ImageNet set of checkpoints, but you can experiment with the others and see how they work and how they compare. So this should be nearly done. Yep, there we go. And then once this is loaded, we can take a look at the sort of PyTorch summary. You'll see that although the model is a lot more complicated than any of the simple ones we made ourselves, it's still a PyTorch model. The encoder is going to be some sequence of layers, right? We can check this out here. We've got a whole lot of output because this is a large model. And they're grouped into different modules and sections, and they've got some extra blocks that we haven't encountered, like these ResNet sections, which is just a sort of more modern improvement on a standard convolutional network. But you still have convolutional layers, you still have normalization and dropout, downsampling. So yeah, it looks a lot more complicated, but it's still just a neural network, and we can still feed data through these different sections. Okay, so let's try encoding an image and see the resulting latent representation. So I'm just downloading an image of a cat here and passing it through the model, right? Model.encodeImage, and we're going to get our Z. And you can see this Z has a shape of 1, because there's a batch size of 1, and our image is 3-channel 256 by 256. Our Z dimension is 256, but then it's 256 by 16 by 16. It's not just a single value like you might see with other GANs. And that's because of this architecture here. It breaks the image down into patches. And so you'll notice if we change the size of our image, right, if we do a 200 by 200 pixel image, we're going to get out a different sized Z. There's still 256 is the one dimension, but for each of 12 by 12 patches. So you can explore how changing the size affects this. I'm going to switch it back to 256 by 256. Yeah, and then you'll notice if you put in something that isn't a multiple of 16, your reconstructed image won't necessarily be exactly the same shape. So that's just something to watch out for. But here, if we take our Z and then we synthesize the output image, and again, you can go look at the synth method in this code block here, but it's just basically running that Z through the decoder section of the network, and we get back an output image, and we can compare the output image with the initial image. Let's just have a look at the side-by-side comparison. So you'll notice VQGAN does a pretty good job at reconstructing this image, right? There's some subtle differences. The whiskers are slightly different, and maybe the fur doesn't look exactly the same. But at a casual glance, it does a really, really good job at that reconstruction. And this is the power of VQGAN. It's able to generate a wide variety of images with really high fidelity. So let's see if we can generate some new images. We're going to create a random Z right? 16 by 16 patches, so it should be about the same size as this previous image. And if we synthesize this, we should see, not a beautiful random image as we might have expected, it's just a random strange purple blob. Okay, so we can look a little bit more closely at exactly what sort of format the Z takes and see, I've got this rand_z function to give us something a bit more similar to what the model expects. But no matter how good you do it, you're never going to get anything really consistent. And this is where VQGAN differs from some of the other generative adversarial networks, in that it hasn't been designed to generate new images from a random Z. It's been designed to work with input images encoded, or to have some additional step, right? In their paper, it's the transformers, some additional guiding component, right? This transformer is going to determine what sequence of Z values, and it's going to construct that and guide that output. So by default, if we just throw in a random Z, we're not generally going to get anything very good looking. But with a bit of effort, or if we have some sort of goal or way of steering that, then we can get some really good outputs. So just a little bit of a difference between this and your sort of standard generative model, where you just want to be able to create plausible images from any input. Okay, so with that little caveat out the way, a quick little demo just interpolating between two images in this sort of latent space, right? Moving from one Z to the other and synthesizing images from all the intermediate results. Not really impressive in this case, but sometimes useful if you want to fill in frames, for example. But anyway, so that's our GAN. We can encode and decode. We can go from some Z back out to an image. And so that's enough for now to then move on to the next big tool in our arsenal. So we've met Clip before, but we haven't really dived in. So let's take a look at the blog post. Really nice persuasive blog post here. And if we want, we can dive into the paper as well. I think this is the right paper. There's one linked from this page. Okay, so Clip has been designed to kind of get around the single type of data limitation that many other networks suffer from. It's designed to be able to handle a wide variety of types of data, both images and text. And the approach is really neat because although it's this really fancy new state-of-the-art thing, it's also simple enough that this one diagram kind of encapsulates everything we need to see. So the idea here is that they've scraped many, many images that have a corresponding piece of text. And this can be the alternative text on a website that's there for accessibility reasons, or it can be the caption on Wikipedia. But one way or another, they know that this image and this text should go together. They're associated, they have the same sort of content. Obviously, it's not perfect, but what they'd like to do is have this model learn how to create a representation of both the image and the text, where if they should go together, they're similar, and if they shouldn't, they're very dissimilar. So to do this, they take a batch of images, and each of these has a corresponding piece of text, right? And you can imagine the second image here might be a tractor or a shoe. And so this first image is a dog. It goes with this caption, Pepper the Aussie pup. And so they have a text encoder and an image encoder, which map the different inputs to a single vector, right? 512 numbers that represent this text, 512 numbers that represent this image. Then they have a measure of similarity called cosine similarity. And you would want the similarity between this image and this text, image 1 and text 1. That similarity should be high because these contain the same sort of idea. Whereas if we look at the second image, right, image 2 of a tractor, say, that is very dissimilar to Pepper the Aussie pup. And so we would expect this similarity between image 2 and text 1, we want a low similarity. So they construct a loss function that basically encourages this. You want a high similarity on the diagonal, image 1 with text 1, image 2 with text 2, and so on, and a low similarity everywhere else. And this is called contrastive learning, very powerful technique. And by training this on millions and millions of images, they are able to learn this embedding space, and they're able to end up in a situation where exactly that desired outcome happens. Images and text that are associated, when you encode them, the encodings are similar. Images and text that are unrelated, when you encode them, the encodings are dissimilar. So we can load up Clip, right? This perceptor is going to be our Clip model. Now they have various image encoders to choose from, so that's why we're specifying one here. This is based on a vision transformer. They also have one based on a convolutional architecture and a couple of other variants of those. But once we've loaded our model, we can then encode some text right? Perceptor.encode text. And you'll see this gives us back this tensor size, batch size 1, 512 values. And if we encode an image, which is very different to this text, right? Very different original form. We encode it. Now we have to normalize it if we want it to be work well. But still, normalize the image, encode it with perceptor.encode image, and our image embedding now looks very much like our text embedding. At least it's the same shape, right? And so this is the first sort of key utility of this. It gives us a way of comparing this image and this text directly because we now have them in the same shape and format. So then with this, as long as we have a measure of similarity, right? In this case, let's try cosine similarity. We can then start to do various tasks. One of the big ones that they highlight is so-called zero-shot prediction. You encode an image and you encode various possible labels and you see which label is the most similar to your image, right? So we're going to do that in code here, loading in our image of a cat, creating our image embedding. And then for each of 3 possible labels, we're going to calculate a similarity and then a loss, which is just 1 minus the similarity. So lower loss is better, means higher similarity, which is the distance between, or the similarity between this image embedding and the embedding of our label. So if you run this, you'll see this sort of loss, right, where lower is better, of our image versus a dog, 0.78, our image versus the text, a cat, 0.72, so that's better, higher similarity, so lower loss, and a sea lion is even worse. So the prediction here is that this is an image of a cat, and it is, you saw it earlier. So this is without having to do any training, just by specifying some text labels, we're able to effectively create a custom image classification setup. So that's a really useful use case, but it's not exactly what we want for art, but still really nice to be able to use the model in that way. So a little discussion here, why did I do 1 minus similarity? You could just store the similarity and then look at the maximum similarity to find out which is your correct label. But in the optimization loops and in the sort of general training loop that we talk about, we often want to minimize some loss. That's the sort of wording that we use. And so by framing this as something to be minimized, 1 minus the similarity, we can then use that vocabulary of loss, and it just seems a little bit neater and more coherent with the rest of the notebook. And now there's an alternative to cosine similarity. You can just as easily, sorry, my tea flask is being used as a nest by a wasp, and it's just delivered its 8th caterpillar. Minor distractions. So here's a different alternative to cosine similarity that seems to work really well, so-called great circle distance squared. And here again, lower value is better. So this is a loss function. So that's Clip. Really good at comparing images and text, or comparing images with each other. Lots of potential applications you can imagine. Just like we found the best label for a given image, you could give a description, a landscape at sunset with pine trees, and then you could compare multiple images to that and pick the one that matched best. And now you have a way to search images with natural language in a really powerful way. It's a really great model. How are we going to use it? Well, we're going to combine this with VQGAN to steer our output and to try and generate something interesting. So we can start optionally with an image or just with random noise. And we're going to encode that into this Z space, right? The latent space of VQGAN. And then we're going to do this little cycle where we decode that into an image, our sort of output image. And then we compare that using Clip to some text, right? A description of the image we'd like to generate. And the closer these are, the lower the loss. So when we optimize, we use the optimizer to modify Z such that the generated image looks more and more like the text prompt, right? So very simple idea, very, very powerful. We're encoding some text, a painting of a jellyfish. We're encoding, starting with a random Z. We're making sure that it's going to be sized to the right size for Clip. Setting up an optimizer that's optimizing this Z value that we've generated here. And then in our optimization loop, we're doing the same thing that we always do, zeroing the gradients, getting our output, right? This is using VQGAN to turn Z into an output image, encoding that image and calculating a loss, here using the cosine similarity, updating our parameters and seeing what happens. And this doesn't take too long to run, and it should, you see the loss gradually decreasing, and at the end of it we get something vaguely jellyfishy, sometimes better than others, but not perfect, and we'll see some potential improvements. So don't spend too long on this one. This is the kind of minimal loop. So let's make a few improvements here. Let's add some transforms. So we're going to run several different modified versions of the output image through clip to kind of smooth out our loss and get a better measure. We're going to save some images to a folder for later viewing. We're going to have a nice display. We're going to have some nice parameters to easily tweak things. And we're going to use our clip loss, the great circle distance squared. So you can see the changes here, adding some transforms, still starting with the random Z, encoding our text prompt, setting up our optimizer, and then doing that same approach, right? Synthesizing our output, in this case doing several variants of that, storing our loss, backprop, optimizer.step, and you'll see this gradually sort of starts from this random image, and over time it gets better and better and more like the thing that we described, which I think was a painting of a jellyfish. So highly entertaining to play around with. This is our sort of implementation of this approach. There's many others that do different transforms and slightly different code implementations, but still very much the same idea. And you'll see that once we add in this clip steering, suddenly VQGAN becomes a really powerful generative model. It's able to produce all of these beautiful, vibrant, kind of interesting images, and do so fairly quickly as well. Now I've just sort of thumb-sucked all of these parameters. I picked a few random transforms from the Torch Vision transforms page, learning rate, number of iterations, all fairly hand-waved. So highly recommend improving those rather than just running with my defaults. Or even better, go and use an existing notebook that's been used by many people and kind of improved and optimized collectively. But you'll see that whichever ones you actually look at, the implementations might be different one to the other. Right, here's one, I think, based on the one by Rivers Have Wings, but heavily modified to have lots of parameters you can tweak. So it'll look very different code-wise, but if you dig in, you'll see that it's actually, okay, they have make cutouts class to do multiple cutouts, but at the core of it, it's going to be very similar. So if we scroll down to, okay, they're encoding their different prompts, they are doing an optimization loop, zeroing the gradients, then synthesizing the output, encoding that via clip, comparing that to the prompts, getting the sum of the loss backwards, optimizer.step. It's the same ideas, it's just the different framing. So once you've played around with our kind of toy demo version, you can either keep using this and improving it, or you can use one of those other notebooks, but now you know what's going on under the hood. Okay, so a few tips on getting better images. If you start from an image rather than that random noise, you can really control the composition and give it a much nicer starting point. So make your own initial images. Can just be a random, like, bad, Microsoft Paint image. So long as there's some structure there, it gives it a better starting point. Then also the prompt that you feed in has a huge effect on the output. So here's the same 4 prompts: mushroom, spaceship, volcano, Victorian house on a hill. But if you add the words pencil sketch, you can see the outputs are very different versus 8K 3D versus concept art or low poly or storybook illustration, right? So you'll see there's a huge variety of images that you can generate, and by just describing the style in text, you can get drastically different results. So instead of a painting of a jellyfish, you could say a botanical illustration of a jellyfish or a 3D render of a jellyfish. So highly recommend playing around with different prompts. And then the good thing with these models is that you can run, computers don't mind repetition. You can generate 50 or 100 different outputs with variants of the prompt, variants of the parameters, and then just pick the one that you like the most. There's no rule that says you have to generate something nice each time, and often it's better to just generate multiple options and see which one you like best. Okay, so some exercises if you'd like to dig into that code and understand it a bit better. Add some more transforms, implement multiple text prompts, so you can imagine just storing the loss from each prompt and then averaging them together before you do the backwards pass. Make it easy to specify an initial image rather than starting from a random Z. Add image prompts, because Clip can compare one image to another just as easily as it compare a piece of text to an image. Then there's a for loop in there that you can get rid of with a bit of optimization if you're good at working in batches. Experiment with adding some different losses. So look at the style or content loss from the lesson 2. See if you can bring that in alongside a clip loss. So lots and lots of things you can do there. We will, in the next lesson, lesson 4, be talking about ways to take this a lot further. So do join us for that. That should be fun. Yeah, and then besides that, do have fun. Please post anything cool that you generate. Chuck it in the Discord for us to appreciate. We've got some cool jellyfish and underwater landscapes, and then of course everyone has their own ideas of great prompts, and there's a lot of creativity that you can do in that. Okay, so that's the main section of this notebook done, and that's got us to the sort of point that I wanted to with this course, where we can sort of read and understand the existing notebooks that people are using to generate this really cool art, which I think is great. Yeah, so now from now on it's just sort of bonus days, adding additional adding additional little bits of learning. Okay, so the final sections in this notebook, GAN training, like I said, difficult in practice. There's a few bits of material linked. This one here has some good information on the ways GANs can fail. And this is a fairly decent tutorial on training your own generative model from scratch. So it's a pretty nice, clean implementation. But yeah, you'll see it is quite tricky to get something that looks really good. Okay, and then this final section, I'll just skim through the code here. I thought it would be worth looking at least one other type of GAN, because there are sort of many variants, and one of the things that we'd like to do is have control over what's generated. And big GAN has been around a while, and the idea here is that instead of just passing in our set of sort of random Z value into our generator, we make its life a bit easier by also specifying to these different subnetworks what class of image we're looking to generate. So instead of trying to generate all possible images, it can learn on a class-by-class basis. And then this also lets us generate images of a specific class. So we encode the class name. There's 1,000 different classes to choose from, different types of dogs, snakes, cars, boats, etc. So we're going to pass that to our model as well as that random Z value. So I've hidden away some code for simplicity. You're welcome to go and read it. But the idea here, yeah, we specify our class, right? What ImageNet class are we working with? And then we specify our noise vector, which is just a random Z, which we'll feed into BigGAN, our BigGAN 128 model, and we'll generate some images. And so you can see here we have a fairly diverse set of German Shepherds. And then there's this extra component here, Truncation. This is just how crazy we go with our Z value. So if we passed in all the Z values with just 0, it would generate one single pretty generic German Shepherd. But as we increase this truncation value, we allow larger and larger deviations from that. And so we can get wilder and wilder results. And you'll see things that start to look less and less like an Alsatian or German Shepherd and more like something completely different. So it's quite fun to explore. You can obviously try different classes. Here's some jellyfish. And you can go pretty crazy with not only setting the truncation to 1, but then multiplying some of these noise vectors with to scale them up additionally, right? So I think this little animation I did, starting from truncation of 0 and then just basically scaling those noise vectors up until we move further and further away from the kind of canonical German Shepherd and into this random unexplored parts of the BigGAN latent space. So fun little diversion there. But the main takeaway from this extra section is that there's many ways to control the output of a GAN. One, you can explicitly tell it the class of image that you'd like to generate. And then if you look at something like ArtBreeder, you'll see that they've also found ways to kind of explicitly set certain parameters, right? Like more or less trees in an image, or older or younger in a picture of a face, or yeah, brighter or darker, greener or bluer, more male or more female, lots and lots of different sliders to kind of explicitly guide the output of their generative networks. So lots of interesting research, lots of ideas. You can plug in various different GANs, combine them with clip just like we saw here, and it's always going to be the same sort of optimization loop. Zero gradients, generate your output, calculate your loss, update your Z values, rinse and repeat, and hopefully get something cool. So that's it for this lesson. I really hope the recording worked this time, and I hope you've enjoyed. We will see you on Sunday for lesson 4, which I'll also then re-record and upload soon after. And that'll be the final lesson in this course. Thank you for coming along so far. And please do post any questions, comments, feedback, etc. in the Discord. Cheers for now.